This is a question to get you thinking about using block RAM memory in other applications other than as pure RAM and ROM. It may not be the most efficient way to implement a counter, but given the outline of the problem, it is better to use this resource than waste it completely. Remember, it may make it possible to move to a smaller device that has block RAMs, but not enough LUTs. So a design is just too big to fit in the FPGA, and the larger device is too expensive. However, 5 of the 12 block RAMs are unused in this logic-intensive design, and you wonder if they can be used in some way. Then you notice that part of the design requires a set of 10 counters with the following specification. Each counter is a relatively simple 9-bit up-down counter used to indicate an angle in degrees. This is slightly complicated by the fact that the counter has an enable, reset, and saturation logic such that it will not count above 359 degrees or below 0 degrees. So, take a minute and can you outline how the counters can be implemented in the spare block RAMs and make the project meet budgets. A hint for you, a counter is just a special type of state machine. And in the case of you're implementing a state machine, your current state is going to be part of the outputs. So you're going to be feeding back some output bits from the Q output back into the actual address. Okay? So stop the recording and take a few minutes and start to consider how this would be implemented in block RAM. It might actually take you a while. It took me a bit to actually figure this out for the first time. When you're ready to hear the answer, start the recording and you can listen to our solution. The solution for this is very elegant. We can implement the counters by using a single block RAM. We simply have to map out this state machine into an initialization table. We chose a block RAM configured for 2K by 9-bit output. The key is that the state of the counter is encoded as part of the memory location. The 9 bits necessary to encode 360 counter values is encoded as part of the next state address. This next state address is fed back to the address lines from the outputs. You see, this is effectively describing a finite state machine behavior because the next state address, or the next incremental count in this case, is generated as an output and fed back to the inputs of the address port. The only thing left to do is build the enable and reset structure into the block RAM. So as you can see from the table, count up and count down are brought into the memory as one of the 11 inputs to the block RAM. Now, the most elegant thing about this construction is that once it's made, it can be used twice. Remember that our original design needed 10 of these counters, but we can make 2 of the counters from one block RAM. That is because the block RAM is dual port and has separate ports. So once a table is used as a ROM, it can be accessed twice. The ROM does not need to be paged if the same contents apply to both ports. One of the concerns is the priority of the control signals. In our case, if the reset is to work, even if the enable is low, then you need to have the additional LUT to resolve this as shown. This design could support an additional control input, the MSB of the address, or you could use this to perform the reset and save the external gate feeding the enable inputs. But this would mean that the enable had to be high for the reset to work, and you could do that with the dedicated SSR pin anyway. You could move the enable to the MSB address, and this would allow the reset to have the highest priority. However, a counter is only a specific state machine. In a normal state machine, you want to maximize on inputs, and hence use the control ports provided. Note that the SSR port can force any value to the output specified by an SR value parameter value. If you had a 32-state state machine, only 5 outputs would define the state. This would leave more inputs and outputs to connect to the system. Although you may engineer the idle state to be zeros, the outputs may need to be a specific value. This is where the SSR value is better than a normal reset. Here is a short list of some of the design tips we just covered about using the block RAM resources. To get the most out of the FPGA, consider converting CLB components into block RAM, especially state machines, large decoders, counter implementations, as we've seen. This is often helpful for designs that are running out of CLB resources and may enable you to move to a smaller device and reduce the cost of your component. Block RAM is synchronous. Also keep in mind the parity bit can be used as an extra output, so don't be afraid to take that output. Choosing an aspect ratio is important for saving resources and good speed, and the core generator will build your large memory with the optimum configuration. Building creative components with the block RAM resources takes extra effort, but it always saves a lot of CLB resources. As I mentioned, finite state machine, counters, and decoders are just some typical applications. Constructing these requires creating an initialization table, which, as I mentioned, is probably the biggest caveat. It's large and it takes a bit of time and effort. But if you've ever done microcoding, you probably won't have too much difficulty. And inferring block RAM has extensive limitations. Most designers like to use the core generator in this case. Now, we wrote a large summary of all the major points we learned in this module. As I mentioned earlier, take advantage of the ILB resources. Don't waste those registers. Minimize the number of clocks in your design, especially in the case if you're trying to think about building a ripple counter or another component that uses a lot of clocks. The more clocks you add, the more congested your routing can come and the tougher it is to meet timing. Use case statements to build decode logic. This simplifies the decoding and saves LUTs and improves speed. Avoid global resets, and we've talked about that a couple of times. Take advantage of carry logic when building decoders. This requires you to build the arithmetic rather than a logic implementation, and it will run faster. Be aware of the number of inputs to your LUTs when you build with a lot of control signals, especially like loadable and up-down counters. Use the best aspect ratio when building block RAM from scratch, or just build it with core generator. To get the most out of the FPGA, consider converting CLB components into block RAM. And we've talked about a number of situations where that could be helpful. Don't forget that. Well, there are lots of places to learn more about FPGAs, and they all start at support.xilinx.com. I want to point out that I referenced several white papers that you might want to check out. They all provide more information on optimizing your design and optimizing the HDL coding for the 4-input LUT. Finally, we spoke about the Xilinx Unified Libraries Guide. It provides insight into the primitives available to designers for each device family. This will explain how to customize the initialization of the block RAM resources and what sizes of block RAM primitives are already available. I recommend you check it out. We also spent a good amount of time talking about the creation of block RAM memories from the core generator. To learn more about this, start the IC tools in CoreGen, select the block RAM memory for customization, and after the GUI opens up, click the Help button. This will open up the block memory generator datasheet. It contains information about device utilization, signals, ports, performance, and the various control options that are embedded within the block RAM resources. Have a look, because the sooner you start using it, the better your results will be. Well, that is it. You have completed the Spartan-3 Coding Techniques modules. There is still more to learn about FPGA design practices, so please consider taking the Essentials of FPGA Design course, formerly known as Fundamentals. Again, my name is Frank Nelson. You've been listening to the Spartan-3 Coding Techniques, Part 2 REL. Thanks for listening.